Now that we've finished discussing spectroscopy and how you can determine the molecular structure of a compound using NMR and IR spectroscopy, I want to turn our attention to the last section of this course, which is electrophilic addition reactions to carbon-carbon pi bonds, alkenes and alkynes. And they proceed by several different types of mechanism patterns. So in general, if you have a polar molecule, AB, where A has a partial positive charge on it and B has a partial negative charge on it, it can add to an alkene. And if you have an unsymmetrical alkene, it will add so that the partial positive end goes to the less substituted end. So we have our electrophile here, and our nucleophile here. And it will always add to the carbon-carbon pi bond, so the electrophile goes to the less substituted end. So our product will have a methylene group attached to A, and B will end up at the more substituted center. The reason for that is that many of these reactions go through a positively charged, or at least partially positively charged intermediate, and when the nucleophile attacks, it likes to attack the carbon that is better able to stabilize that positive charge. So there are a whole bunch of different possible AB compounds that we can add across our carbon-carbon double or carbon-carbon triple bond. Perhaps the simplest one isn't a polar pi bond at all, it's hydrogen. So we already know from previous discussion that if you have a carbon-oxygen pi bond or a carbon-carbon pi bond, it will undergo catalytic hydrogenation with H2 gas, some kind of active catalyst in the nickel, palladium, platinum triad, the Alkynes catalyst in this case. And if you do that at increased pressure, to use Le Chatelier's principle to drive it forward, generally in an alcohol solvent, sometimes with heat, but often without heat, you can succeed in reducing the alkene to an alkane. If you have a triple bond, the same set of reaction conditions will reduce it to an alkane as well. So if we were to take 2-pentyne and react it with our hydrogen gas, some kind of nickel triad catalyst like 10% palladium on carbon, at an elevated pressure in a solvent, usually an alcohol, we can add 2 moles of hydrogen across that carbon-carbon triple bond and convert 2-pentyne into pentane, just as we can take cyclohexene and convert it to cyclohexane. So hydrogenation, catalytic hydrogenation, is a way of taking alkenes and alkynes and producing from them alkanes. Generally not just an alkane, generally somewhere in a larger molecule that has other functional groups present as well. In fact, this catalytic hydrogenation process is the route for determining the relative stability of different kinds of alkenes. It's how we actually know that the more substituted double bond is more stable. It's how we actually know that the cis alkene is less stable than the trans alkene. So for example, if you take 3 isomers of butene, one butene, cis-2-butene and trans-2-butene, all of these can undergo catalytic hydrogenation with H2 gas and the catalyst, maybe radionickel, at some elevated pressure in an alcohol solvent to yield the same product. They will all yield butane as the product. And here I'm using the E and Z nomenclature, where E stands for Alkyne. It tells us that the two large substituents are on opposite sides, and Z stands for susamin. And tells us that the two large groups, the methyl groups in this case, are on the same side. Remember that this is a more general nomenclature than cis and trans. Cis-2-butene and trans-2-butene work very well here, but if one of these substituents was not hydrogen, then we would have to use the E and Z nomenclature. So we have hydrogen gas and pressure, and we're converting all of these to butane. And the amount of energy that's liberated in the process of doing this, in all cases, we're forming sigma bonds, which are more energetic than the pi bond that we're breaking. So these are all exothermic heats of hydrogenation, but the heat of hydrogenation is quite different. For 1-butene, the heat of hydrogenation is minus 30.3 kilocalories per mole. For cis-2-butene, or Z2-butene, it's minus 28.6 kilocalories per mole. And for E-butene, it's minus 27.6 kilocalories per mole. And this graph and the numbers are on page 476 of your textbook. So we see that we actually release less energy when we hydrogenate E2-butene than we do when we hydrogenate Z2-butene. And both of those result in less energy release than when we hydrogenate 1-butene. So if we wanted to put these to scale on an energy diagram so that we could show the difference between them, we would find that since it releases less energy, it's at a lower energy to begin with. So 1-butene is here, and then 1.7 kilocalories per mole lower is cis-2-butene. And another 1 kilocalorie per mole lower than that is trans-2-butene. So that when they're all reduced to the same substance, more energy is released from hydrogenation of 1-butene than hydrogenation of cis-2-butene, and more energy is released from hydrogenation of cis-butene than trans-2-butene. This tells us that trans-2-butene starts off 1 kilocalorie per mole more stable than cis-2-butene, and that can be accounted for by the steric hindrance of these two methyl groups interacting with each other on the same side of the molecule, where there's no steric hindrance of the E2-butene. The 1-butene is another 1.7 kilocalories per mole higher in energy, and that's an electronic effect because here there's only hyperconjugation from one alkyl group. None of the hydrogens are capable of hyperconjugation. And in these cases, we both have two alkyl groups. So this is due to hyperconjugation. And this is due to sterics. And we know that hyperconjugation will stabilize molecules, and steric effects will destabilize molecules. And the hydrogenation process allows us to determine the relative stability. So this is how we know that a tetrasubstituted double bond is more stable than a trisubstituted double bond, and a trisubstituted double bond is more stable than either a cis or a trans disubstituted double bond. And a disubstituted double bond is more stable than a monosubstituted double bond, like this vinyl group that we have here. Would be just ethene. So hydrogenation of CC double bonds and CC triple bonds can produce alkanes, and it can also allow us to investigate the energetics of the different alkenes. The pi bond in the alkyne is more electron rich because there are 6 electrons being shared between the nuclei than an alkene, where there are only 4 electrons. So one would expect the alkyne to be more reactive towards hydrogenation than the alkene. If that's true, the greater electron density, the fact that the alkynes are more electron rich than the alkenes, it should, in theory, be possible to stop the addition reaction halfway at adding only 1 mole of hydrogen and thus generating alkenes from alkynes. Anytime that your intermediate is less reactive toward the reaction conditions than your starting material, it is theoretically possible to stop at that intermediate and not go any further. This is the opposite of the situation we have when we are oxidizing a primary alcohol with aqueous acid and chromium-6 reagents, where the aldehyde intermediate is actually more reactive to the oxidation conditions than the primary alcohol. And that makes it impossible to stop, because your intermediate is going to react faster than your starting material. But in this case, we have an intermediate that's less electron rich, has fewer electrons between the nuclei, and therefore less nucleophilic. And if it's less nucleophilic, it should be possible to make it stop. So it should be possible, for example, to convert 2-butyne to 2-butene, cis or trans 2-butene. If we use platinum oxide or 10% palladium on carbon or radium nickel for this at elevated pressure, we will find that it's not possible to stop. The cis 2-butene will react further. But if we use a deactivated catalyst, that's reactive enough to react with the more electron-rich alkyne, but not reactive enough to react with the less electron-rich alkene, then we'll be in business. And since we know that the alkyne is more reactive than the alkene, we know that it will be possible to design a catalyst that is only capable of reducing the alkyne and not capable of reducing the alkene. Hydrogen gas is still the source of hydrogen, but the catalyst now has changed. Instead of using 10% palladium on carbon, we're going to use 5% palladium on barium sulfate or calcium carbonate. I think it's calcium carbonate in your textbook. So the sulfate instead of carbon black. And then, importantly, we put in 2 two catalyst poisons, lead acetate and quinoline. And quinoline is an aromatic compound of nitrogen. It's the aromatic nitrogen that actually interferes with the reactive sites. So these two things, the lead acetate and the quinoline, are catalyst poisons that reduce the reactivity of the catalyst, and switching the solid substrate that the palladium is deposited on also helps. So these two catalyst poisons, it's the aromatic amine, that's the business end here, and it's the lead here, the heavy metal. That's the catalyst poison there. The acetate, of course, most lead compounds are insoluble, so lead acetate is a logical source of lead 2 acetate. This combination, 5% palladium on calcium carbonate, lead acetate, and quinoline, is referred to as the Lindlar Catalyst. The Lindlar Catalyst is not the only deactivated catalyst that will cause alkynes to reduce specifically to the cis alkene and stop, but it is the one that's described in your textbook. 5% palladium on calcium carbonate, slightly basic, and with an additional metal in there, lead acetate, and quinoline as catalyst poisons. This compound is quinoline, QUINOLINE. It's two aromatic rings fused together. So we can stop, and you'll notice that it's stereospecific. And it leads to only the cis isomer of the alkene. That's actually a more general truth of catalytic hydrogenation, is that catalytic hydrogenation is always a syn addition. Where the syn addition means that the two groups, in this case both hydrogen, come from the same side of the molecule, the same face of the pi bond. So if we were to take cyclohexene, and instead of reacting with hydrogen gas, we were to react it with deuterium gas, D2, under the usual catalytic conditions, 10% palladium on carbon, increased pressure as solvent. We would end up with a molecule that had the two deuteriums cis to one another. Since there's no ability to rotate around the carbon-carbon bond when it's fused into a ring like that, we can determine that the two deuteriums must have come from the same side in the molecule, which is a syn addition, and in this case, the syn addition yields the cis isomer. That's not always true. In this case, the two groups that are put on are both bigger than the groups that were there to begin with, and so this is a cis isomer from a syn addition. It's possible to get a trans isomer from the syn addition if one of these groups were actually lower priority than the other group attached. If this were a methyl group, for example, the methyl group would take precedence and we would not have the cis isomer. But in this case, it's a syn addition yielding the cis isomer. And in this case, it's a syn addition to the alkyne yielding the cis isomer of the alkene. To understand why that's true, we have to think about the mechanism of this reaction. And although that mechanism is complex, happening at the surface of the metal, what is known is that the hydrogens are both delivered from the metal surface. So if we have a metal surface here, And we know that the nickel triad metals, nickel, palladium, and platinum, are particularly good at absorbing hydrogen to make interstitial hydrides, and that some of those hydrogens will be surface bound. If that's true, and you are an alkene or an alkyne, your pi bond is going to donate into one of the empty d orbitals of the metal surface, and you are going to be approaching so that the two hydrogens can't help but attach to the same side of the molecule. It is thought to be a stepwise process, so that there will be an intermediate where one hydrogen is added, and the molecule is bound through the pi bond still to the surface, but the molecule doesn't leave, right? It doesn't freely rotate, so that the second hydrogen will be added to the same side as the first hydrogen. There's no way you can hit both sides of your head on the table at the same time, so if your hydrogens are both attached to the table, they're both going to end up attached to the same side of your head, or in this case, the same side of the pi bond. So this is a syn addition, because the two hydrogens are both delivered from the same location. Which is useful, because it allows you to make one stereoisomer specifically. As long as you want the cis isomer of the alkene, cis-2-butene in this case, that's great. But what if you were to want the trans isomer? Is there a set of reaction conditions that will stereospecifically generate the trans isomer? Since I bring it up, the answer is obviously yes. But it can't be a catalytic hydrogenation process, because anytime you have a catalytic hydrogenation process with a heterogeneous catalyst like this, your hydrogen is going to be delivered from the surface. So we'll have to come up with a completely different type of reduction reaction. So if you want to take 2-butene and make from that stereospecifically trans 2-butene, so we get the other stereoisomer, what we're going to have to do is use a different reduction, and the solution to the problem is to use lithium solid and ammonia liquid. This is the dissolving metal reduction, which you're familiar with. Because it's the same set of reaction conditions that we saw before that allowed us to take a disulfide and convert that disulfide back to the thiol. The dissolving metal reduction allowed us to do that. In this case, it's 2 steps. The aqueous acid workup is required because the intermediate is the lithium salt of the thiol, CH3S minus in this case. No second step is required in the case of reduction of 2-butene to trans-2-butene, although an aqueous acid workup is normally put in there to react with the excess ammonia that's, or amide ion that's produced in the process. So what's the mechanism of the dissolving metal reduction for the reduction of an alkyne? We've already looked at the mechanism for the dissolving metal reduction of a disulfide, but what happens to the alkyne? We know that the dissolving metal reduction is effectively an electron floating around in solution, surrounded by the partially positive end of the ammonia, we call the solvated electron. And I'll just show two salt molecules there, but it is surrounded. So the electron will be attacked by the pi bond. The result of that will be for one of these electrons to go in each direction to produce a radical anion. This electron and when you put an electron into the pi star orbital, that going in the wrong direction. When you put an electron into the pi star orbital, you break the pi bond, or at least substantially weaken the pi bond. There's a lone electron here, it's not particularly happy. It's easily going to pick up a second electron to form a dianion. So you've effectively just donated two electrons into the pi star orbital, thus completely breaking the pi bond, because now the bond order is reduced by one. And there are two reasons why it likes to form the trans isomer. One of which is that we like to maximize the distance between the two negative charges. To minimize repulsion. And the other is that the two methyl groups would like to be as far apart as possible to minimize sterics. So we've got a combined electronic effect and a steric effect, which both tell us that the trans isomer is going to be the one that's produced. The remainder of the mechanism is for the alkynyl anion to now pull off a hydrogen from ammonia. To generate a monoanion and a lithium salt of the amide. And then this will happen again, a second molecule of ammonia will donate a proton to form the final product and another lithium amide. And those lithium amide molecules or salts, will be quenched. We can calculate the equilibrium constant for this reaction and show that the equilibrium lies well to the right if we know the pKa of the hydrogen that was just added, which is about 44 on an alkene, and we know the pKa of the ammonia. This is an acid-base reaction where ammonia is acting as the acid, the vinyl anion, or the alkynyl anion rather, in this case, is acting as the base, and amide ion is the conjugate base, and the alkene is the conjugate acid. Since the pKa of our conjugate acid is 44, which is significantly larger than the pKa of our acid, this is a much weaker acid. In fact, it's about 9 orders of magnitude weaker, which means that the equilibrium constant for this reaction is equal to 1.0 times 10 to the 9th. And the reaction goes to completion. The alkenyl anion is a stronger base than amidion. Amidion is a strong base, but the alkenyl anion is even stronger. It's not possible to calculate the equilibrium constant for this first reaction because we don't know the pKa of this hydrogen on the alkenyl anion, but we can assume that it's higher than the pKa of the hydrogen on the neutral alkene. We can assume that the dianion is a significantly stronger base than the monoanion. So if the equilibrium constant for this reaction, the second proton transfer, is 1 times 10 to the 9th, the equilibrium constant for this first reaction is much larger than 1 times 10 to the 9th. So unlike the case where we're reducing the disulfide to the thiol, in this case, ammonia is a stronger acid than our product. Right? When we reduce to the thiol is a stronger acid than the ammonia. So the proton doesn't actually add to the sulfur until the workup step in aqueous acid. So it's now possible, using the right reaction conditions, for us to take an alkyne and generate an alkane using raney nickel or platinum oxide or 10% palladium on carbon, to generate a cis alkene using hydrogen in the Lindlar Catalyst, 5% palladium on calcium carbonate with lead acetate and quinoline as catalyst poisons, or typically by using a dissolving metal reduction with lithium or sodium in liquid ammonia.